Oh, yeah. Allowed to screen share. Mark, okay, good.
Not quite as I wanted. Okay, so now, second trial. Now it works, right? Is it full screen now?
Yeah, I think this is where we kind of stopped last time.
Yes,
Yeah.
so, and you see full screen now?
Yeah.
Okay, very nice. How's the audio? Yeah, because I have the window open.
No, it's okay.
Good. Yeah, so this is where we stopped. We tried to translate what we learned for ordinary differential equations, reconstructing network topology from my phone is ringing again. Network topology from recordings of trajectories which are generated by ordinary differential equations or time continuous systems to those time series which are consisting of event times only, which are spike patterns. And like this is just let me
I'm sorry, we can't hear you.
now?
Yes.
Yes.
Good. Sorry. Yeah. The typical recordings you get from neuroscience are extracellular recordings, which means that you see rapid voltage variations near neuronal cells, and which people in experimental neuroscience translate to event time. So essentially they record timings of action potential sending, like when the signal from one neuron is sent to another one. And if you do that for many neurons, you get these spike patterns. One neuron, and here's neuron N. And for each neuron, you have a sequence of event times. This is time. This is time. And this is neuron ID. And you see, well, we had examples of regular, intermediate, and very irregular patterns. And then we closed last time saying that if you pick pieces of, if you have many data and you have the luxury of picking those trajectories which are close by, which are grouped closely in state space, in the state space of inter and cross event times or spike times, you are still performing reasonably well for irregular patterns. In general, that's not true. Like if you have very irregular patterns and you just pick any, you have, for example, only a few data, or you pick any subset of the data, you get poor performance. Remember that 50% here, AUC score means essentially not better than guessing something. Okay, and second last time we had similar reconstruction task where we had recordings xi as a function of t sampled at certain times, and from many of those trajectories we could infer the topology. And here we used the state space xi, xj, and then what we call a dynamics space, where you have, in addition, an estimator for the rate of change of variable I. And we translated that idea to spiking events, which well, you get these types of spike pattern, and you get the topology from inter and cross spike intervals. So let's call them I don't know, T maybe. So that's like this. We translate the same idea that you have some smooth surface here, and you want to find directions into which the surface does not change. In other words, dimensions along which about which the interspike interval is independent. Meaning the same here as the rate of change of variable I is independent of some variable xj. For example, it would mean that it's constant in these directions. It may vary in other directions, but it's constant in these directions. And here, the same, if it's constant in these directions, it does not depend on neuron K, this particular neuron. In both cases, we had time series. So we had, this is time and event times, like certain discrete time events recorded against time for different neurons. And here you do the same for different systems, different variables. Both of it is time series, but sometimes you do not have time series. And we'll go to try to understand that today. What happens if you don't have time series? You only have the collection of points that have been sampled. Okay, so it's equivalent to saying you don't have the time series instead of very long time series. You only have, for example, the histogram. You know where if you plot this is xi, and you have a histogram of how many times a certain xi occurred. Actually, you have much more because you have combinations of state vectors, so it's a high-dimensional histogram. Yeah, this is like the third part, and then there will be a fourth part, which is again a forward problem of predicting nonlinear responses and tipping points in network dynamic systems, or actually we'll work through one-dimensional example and just takes a network example as a motivator. Okay, so assume now you have the differential equation xi dot is some deterministic force fi of x plus some noise, possibly. And you do that in different experiments where you can drive it. And in the simplest case, I mean, all of the studies I have presented can be generalized or attempted to be generalized with time-dependent driving forces and all kinds of other complications. Here, the driving force is only time-dependent in the sense that we switch it on and then we leave it on. We switch it on from 0 to a certain value, I, and this value depends on f. Here's time 0. And only we consider time series after time 0, so we have essentially a constant parameter which we change. And that's actually the simplest setting, as you'll see later. Sorry for that. Just move it. So the idea is there's external driving. What does the external driving do? Well, somehow you have a distribution of points in state space, and somehow if you drive the system, you can imagine that that distribution is moving with it. If you drive it slightly, it might be moving only a slight bit, right? Of course, if you drive it strongly, it might go wherever and go to other stable states or not become stationary at all. Things like that can happen, but assume it's stationary and assume it only changes slightly with small changes of the driving. Then how that changes, again, as our ideas before, depends on the topology. It depends on who is interacting with who. In other words, on the functional form of the f's. Remember that dfi dxj is constant 0 is the same as saying that xj has no influence on I. Okay, this variable xj does not change the rate of change of I. So if different driving signals cause shifts, which in turn depend on the topology, again, the same idea as last time, we have hope to extract features of the topology, and this time I mean again the structure, like who is interacting with whom in this sense, when we observe the system under different driving conditions. And this again is work with José Calzadiego and in particular Mohr-Nitzan a couple of years ago. The idea is like this: you have a network dynamical system which you don't know, it's in a black box, and you drive your system. And in the simplest case, you drive everything with a constant, but it could be I dependent. Actually, it might be, well, index dependent. And then you do different experiments with different driving signals. Okay, this is why the m, small m, indexes the experiment. And you have recordings, and all of the recordings you get, you accumulate to your collective distribution. So this is like a noiseless distribution of states, but you have no time information. Okay, just the only thing you know is that somehow these states have been sampled. You can think of it that if the trajectory is in some state space, and it activates a certain marker. So the only thing you have at the end is after the experiment you can look, and you look which markers have been activated. And this point cloud, it does have a center of mass, an average. And the center of mass will depend on the experiment. So if you do a reference experiment, that's what we call it 0. It's our reference, but you can take any as reference. We just label it like that. You compute the center of mass, which is just for physicists, the average, and just the time sampled average of all points. Zoom is delayed today as well. It just informed me that you can see the slides. That's the time average of the points recorded. And so you get a reference point. You do it again with another experiment, and then you shift your point cloud somehow. And you might deform it a bit as well. But the point is, the main point here which we exploit is that the center of mass will be shifted. So you go from here to there. And the idea is, like, from different experiments and different errors you observe under different experimental conditions, if you evaluate that, there is some chance that you get out the topology, because where it shifts depend on the topology, they depend on the form of f, right? So heuristically, and it's really heuristic, it's not, we can't prove it. Well, we could attempt to prove something for very simple systems, but in general, I think it's hard to prove where it will work and where it won't. But to get the idea, it's somehow reasonable to assume that it could work, okay? We now linearize this f about the center of mass of Z0. Okay, so in other words, we approximate f in this picture in the region of state space around a given point. And that's our reference point. Okay, then you take all the derivatives and the difference of the actual state samples relative to the offset point, which is a reference, the reference coordinate. Then there's noise, and then there's the driving signal. The most important aspect here is that the driving is not only constant, but it's actually additive. You could imagine you drive it somehow, so you tilt f in other ways, which might still be possible, because if for small signals you can then Taylor expand that in the driving signal. We didn't do that, but in principle it should be the same mass. So this is really the simplest system. conceptually some system to show how reconstruction can work. So now you can see what is actually known. These xi dot we don't have because we don't have the times, and also we don't have the xjm. But we do have the averages. So we average the entire equation. We do like from here to there, we do an average over time, okay? We sample all our data points, then we get the rate of change of z. Here it's a constant anyway, so the average over constant is a constant. The only averaged thing which appears in addition is this center of mass. Sorry for that. And you notice that this is going to like 0 because we assume that somehow the noise doesn't have an average bias. Otherwise, you can't distinguish that part, like the constant part of the noise, from the constant part added to f. There's no way you can physically distinguish it. So we assume the average of the noise is actually 0. It might get complicated, for example, in real situations where the noise may have long-time correlations. So, and then if you measure too short interval, then although your noise factually has average 0, if you computed the ensemble average, the time average up to your chosen maximum time, capital T, is actually not 0 if there's long time correlations. So we assume it's 0, and then we take the difference. Well, this one you also don't have, right? You don't have the rate of change of z. We have no time evolution of z actually. But what we do have is a rate of change of all the z for all the m's, for all the different experiments. So we can compute the differences to a reference observer. And the difference should be 0, right? So this one is 0. Ask for it because that's the change of the difference to my reference point. So the only equation you're left with is this one. This one equals 0. Let's see where I have it. And it also you use the difference to get rid of this constant term, which you don't have because you don't have f, right? We don't know the dynamical system, so you don't know f. This is unknown. And you get rid of the unknown term by taking differences. Now you bring one to the other side and you call this delta z. Then you have minus I vector collected over all different experiments is delta z vector over all experiments times, well, the coupling matrix, which is just coding, short form for this derivative, which we have no clue of knowing because we don't know f. So the only thing we want to know is now j, right? J is like something like the weighted adjacency matrix.
Sorry, when we're taking the difference with the reference observable, are we assuming that the driving at the reference is 0?
Yes.
Okay, or yeah.
If it's not, it's not a problem because if you know it. So the main thing is you need to know it. Right? This one needs to be known. If you know it also for the reference, then you just subtract it. You get a difference signal. That's the same thing. The most important thing is that whatever here is here, you know.
Okay, thank you.
You're welcome. Okay, now we want to solve this equation, understanding which of the JIJs, which of these entries are 0 and which are not. The 0 entries represent non-existing links between node j and I, and the non-zero entries represent existing links. I think I have, yeah. And a simple way of trying to solve that is because it's a partially constrained equation. So in general, it might have many solutions. Like if you have too few restricting equations, and you have of the order of n squared variables, which are all the j's. And if you have, so n variables per unit, and if you have less than n experiments, you might run into trouble. A typical way of, or if you have more and you have noise, you also, leftover noise, you also want to somehow minimize the difference. So what people do in a standard way is try to, these are now axes of, two of many axes of this vector, okay? That represents the possible state space of all j's. You can imagine there are more dimensions here. And now this one is a linear, it's a equation for a plane. Equation for plane or hyperplane, right? Hyperplane. So a high dimensional plane. And you might say, okay, maybe it looks like this. Okay, this is some plane. Which restricts the possible solutions to this plane, right? All of the j's which are consistent with my measurements, in other words, with the observed z and the known driving signals. Yeah, you drive it, you observe the shift in the center of mass, and then you get constraint equations. All of the solutions J are on this hyperplane. And a common way of identifying one solution, I mean, there are now many solutions. For example, there's this solution where Ji2 is 0. So the link from 2 to I is non-existent. Let's maybe draw it in another color. So this one is Ji1 not 0 and Ji2 equal 0. In other words, if you have your node I and the node 1 and 2, there's a link here, but there's no link here. Okay. There's nothing from 2 to I. There's another solution, the blue one, where Ji1 is 0 and Ji2 is not 0. Would be this one. There's nothing from 1, and there is a connection from 2. Again, what does it mean? That means that dfi dx2 is not identically 0. And of course, there might be other variables in the other dimensions which I don't plot, like Ji3, Ji4, and so on. And there's a third solution, actually many of them. I know, like maybe this one, where Ji1 is not 0 and Ji2 is also not 0, and it represents this situation where both of the guys connect to I, 1 and 2. Now, which of the solutions to select? There are infinitely many. Actually, there's a typically high dimensional space. It's a plane, right? It's not only line in high dimensions. there's a high-dimensional space of uncountably many possible solutions, all consistent with all of our measurements. And we only have our measurements. So which one do you take? And one standard way is like minimization of a norm. This is a minimum over the sum over k, j I k squared. And that's called, so on that hyperplane, this point is the point with minimum Euclidean norm. It's called L2 minimization. And the generic solution is this one. Generic, like the typical solution you get if you do this minimization, if you have any kind of random plane here, hyperplane, you get and you ask for that point on the plane which has the smallest distance to the origin, smallest Euclidean distance to j I equals 0. You typically get like a fully connected network. That's what you get. In reality, well, if you know you're talking about a network, not all to all coupled. Network. You can also say that you're looking for a sparse solution, like with many of them 0, many j I k equals 0. How do you do that? Let's go back to red. You have the same problem. You have ji1, ji2, and you have this plane. And now you're looking for the minimum L1 norm. Min L1 norm, which is this guy. You are looking for that solution which has the smallest distance to the origin, but in another norm. And how does it look like? Let's do it green again. So this guy is a sphere in J space if you measure distances with Euclidean distances, in standard norm, standard 2 norm. This object and its generalization to high dimensions is a sphere in L1 norm. So it's not drawn exactly nicely, but it's supposed to be. Let's repair it. It's supposed to be the set of points which are equidistant from the origin in this one norm. Okay, this norm is a distance. It's a one norm. It's a sum of absolute values of the vector, and that's a set of points. Also wrong here. That's a set of points equidistant, supposedly equidistant, from the origin in this node. And this gives you, observe that this gives you a what's the wrong one? It's confusing. Sorry. Let's not do it green, let's do it blue. That's the wrong one. So this is a blue point. That's the set of points equidistant to sphere in one node. And observe that once you do that, you get corners. Corners of this simplex, okay? And the corner is something where many entries are 0. So exactly what you want. You're looking for solutions that are sparse. You take the L1 norm, you minimize it, and what you get is a solution which has many 0 entries, and that means a sparse network. So many of the entries are 0, others are non-zero, and the non-zero ones are those you want to know, and the 0 ones you want to know. They are actually 0. Of course, that's an assumption. It assumes that somehow the world is built like that, like you find it in a consistent way, but that's the minimal effort solution consistent with all my measurements. So the red line is a consistency requirement. All solutions are on here. All solutions, shouldn't do the blue. All solutions consistent with my data, with my measured data, on this hyperplane, and one solution is particularly interesting, and that's this one. Any questions about this?
I guess things are okay.
Good.
They've seen it in different flavors in Ridge and Lasso, I think.
Yeah, very nice. Okay, and these are just illustrating the results a bit. So we have given a network which is actually sparse. There is there's this diagonal, meaning there's a self-coupling term in my differential equation, and these are receiver operating characteristic curves, and the area under these curves for a given noise level is this AUC score. So you see that if the false positive rate is 0 and the true positive rate is 1, you're jumping up this corner, and then it's essentially perfect reconstruction. I believe these are 30 nodes, I don't remember, 30 nodes. And you see that it's pretty close to 1 already for, well, less than 30. In the noiseless case, if there's noise, it gets, well, reasonably worse. It would look like this. The red curve would probably look like that. In other words, it saturates below 1. And that's, well, that's not surprising, because you can't exactly find the solution if you have only 30 measurements for a network of 30. And this one tells you the number of required experiments. Of course, that's up to you, like what do you want to require? For example, you could require that my quality of data of reconstruction is like 90% here, and then you can ask when such a curve at a given noise level crosses that 90% curve first. The main point is it does increase with noise, but it's not drastic, right? It's not jumping away. So even if with moderate noise levels, you need of the order of 30 or less experiments. Might actually be not 30, otherwise it would go. Anyway, It has also the potential, as before, as for the spiking networks last week, of revealing, activating versus inhibiting coupling. So instead of only finding which couplings are present, you can check of which are positive and which are negative, and then you have to think about what positive and negative means. And for us, positive actually means derivative positive, meaning that it activates in contrast to the spiking systems. And it also reasonably, with the number of experiments increasing, it reasonably improves performance.
Mark, just a question. I mean,
Yes.
this whole formalism is presented for ODEs. Again, the question remains like one can do the modification for maps, right? And just average over.
Yes, you should be able to do that for maps. The main requirement here is that you measure something stationary, because if you measure different parts of a transient and you don't know where you measure in different experiments, then you have no clue what you're actually doing.
Yeah, absolutely.
Yeah, but it works for maps the same. We never wrote it up, but it's actually it's an easy paper, I guess, because this one is.
No, we're thinking of something. Maybe we can catch up.
No, this one is really it's an easy thing, because there are so many maps, and no one, as far as I know, maybe I missed something, but no one did that, I guess. Now like that's another type of system where for each unit we only measure, we have access to one variable, but we know there are 3 variables. But you don't have to know, but in our case we do know. And we only evaluate the interaction among those variables. The important thing here is that these actually interact, like these variables directly interact. It's not that other variables interact in the background. There's nothing like this, okay? And of course, in reality, you can't know. If you don't know in a model or how your different compartments or different variables in a given unit interact with other units, then you have hard times. But in just showing the principle that the number of experiments increases your quality, and of course, you don't see the same performance because you have less knowledge. So it's not surprising that your AUC curve is below the original one. Now you can do that for real models again, as we did before. Circadian clock of Drosophila, and look at this. It drops with noise level, also unsurprising. So the overall take home is that we can transfer, that was essentially from last time, right? We can transfer the idea of invariant directions in dynamic space to invariant direction in the event space. And that enables us to reconstruct topology even if you do not have access to the internal variables, like for the neuron, it would be the voltage variable, which fluctuates and then crosses the threshold, but only to the event times where it actually does cross threshold. It still required time ordering of state space points, like time series, both of these methods. And this may be overcome by averaging and combining with linear response heuristic, which I just showed you. So you can, under certain conditions, and actually there's a big caveat because it is heuristic, the other one is just assuming somehow everything is in a linear relation and it interacts in a fine way, and somehow there are no other influencing variables and so on. Because that's not true in reality. It is limited. And if you do not know the system, you don't know whether it's true. So that's somehow hard because you can't extract, to the best of my knowledge, there's no method to extract from the data whether your result is reliable or not. So that's really an open problem. I think it shouldn't be impossible, as it was for the topology reconstruction in the earlier lecture number 2. But we don't have progress yet. And it's an important point. Like if you could do that from data, if you could infer topology from data and tell whether your inference is reliable or how reliable it is, that would be progress. I don't stop here. I just go to the next slide set, if you allow.
Could I ask a question?
Yes.
Like all the examples we have done so far, for example, so this one in the Drosophila case was where the readout in the end is the concentration of some species, which in the end is what we consider the node of a network. Am I right? Like in the Drosophila example.
Yes, it's like the state of the variable, and in the Drosophila, it's a concentration of something.
It's a concentration of something.
Yeah, but it's not necessarily, it's anything, like everything you can measure.
Yeah. Is there any work done with that includes the spatial distribution of, for example, this concentration or the readouts that you have?
I don't know specifically whether there's something done on spatially distributed networks, but there is something. There's a bunch of literature on reconstructing. For example, if you have not a collection of ordinary differential equations, but you have instead partial differential equations. So you have a field of variables. There is work in particular by Nathan Katz, for example, and Steve Brunton. They have done a lot, and also others.
Could you write the name down
yes.
in the chat, for example? Because thanks.
Can I do that? Yeah, probably again. I see Steve and Brunton. Yes, they also did many works together. But if you look there, if you look up their names, you will find essentially all relevant references.
Thank you so much.
On PDs. But I think, I mean, in biology, for example, I assume you're from biophysics.
Mm-hmm.
In biology, you're also often have the situation that you have something spatially extended, but it's not continuous. Like, okay, you have so and so many segments of an organism, and you have or an organ, and you have like 27 or 12 or whatever. And then it's not clear. In principle, you could write it down as in the same way because you have neighboring interactions, like neighbor-neighbor interactions. But then if you write that in the same formal way as here for networks, and you have other network interactions, like with the inner of the organism or something, one will suppress the other. So in other words, like for example, if you measure I'm just imagining now a worm, right? If a worm with like so many segments, if you measure the influence of the first segment on the last relative to the influence of whatever one variable in the first segment to another variable in the first segment, and this is probably much stronger. So you could formally mathematically write it down as one network, but it wouldn't help you much. So you rather write many networks and couple them in addition with some, well, heuristic again, coupling variables, and try to make progress from there. And that is, as far as I know, in contrast to partial differential equation, that is probably an open problem as well. Like if you have, in particular, if you have heterogeneous coupling or something, segments couple not identically to each other, then you should run into new research fields. So if you have a specific problem like that, which is not partial differential equations, let me know.
Okay, thanks.
Or just work on it.
Marc, may I ask a question as well?
Sure.
So the treatment started with the X as a variable and moved on to the Z, which is some sort of average. Is looking into different moments of the time series something that gave other, like, more insights on the interaction matrix? So instead of looking at means, I mean, that the mean could be a good thing to look at if the distributions are somewhat Gaussians, but if there's like heavy-tailed, did you look into like higher moments?
No, we didn't. No, we didn't look. We just know from experience that heavy-tailed is always a problem. The same is true for if you use the same method for all nodes in a network, and the network itself has, for example, heavy-tailed degree distribution.
Yeah.
You also run into problems because you can't reliably reconstruct degree 5 nodes and degree 5,000 nodes if you have the same kind of threshold. It just don't work. Yeah, so it's just hard. I don't know whether anyone can do this.
Okay, thanks.
I mean, of course, if you have arbitrary amount of data and so on, it's always possible to do it in principle. But in reality, it's you're somehow constrained, and then it's much harder than reconstructing a relatively homogeneous system. On the other hand, like, for example, the Drosophila here, that there are actually different types of variables with different numerical values. So it may vary an order of magnitude or two, but if you have many orders of magnitude, which is a typical case in power laws, I think basically we're doomed, or we need lots of data, lots of processors. So now it's gone again. So this is now work with another set of people. Moritz Timme is the PhD student actively engaged on the topic since several years, more than 2 years. There's Gwendoline Quasbart to be master student, and Julian Fleck, and also Malte Schröder, and a few other people who have been involved in parts of the work. And now the remainder of today's lecture and this small lecture series is again on forward problems. So the question is, you have a network which shows collective dynamics. And the question is, can you predict its responses to external driving, which makes the network a non-equilibrium system? In particular, we are interested in asking or in predicting where this system has a tipping point as a function of the amplitude of a driving signal. And
Marc,
as
you start, we're not seeing the screen if you're sharing something.
Bad. Yes. Okay. Thanks for that. Okay, it's about non-equilibrium network dynamics and the prediction of generally nonlinear responses, as well as tipping points, which are super nonlinear in the sense that you lose your entire qualitative state at some point. And we do that as a function of amplitude of a driving signal. And again, as you'll see, we pick like the simplest possible system which shows a phenomenon. But the phenomenon itself is very general. We have been surprised, and maybe some of you knows, but I've been talking personally to like 15 scientists from scientists, mathematicians, and engineers, none of whom could tell me, okay, it's in this textbook from the 80s, but it should be read somehow. You'll see why in a minute. You didn't find it, so if you have any reference which solved that problem before, let us know, please. Okay, all of the networks I've presented in our introduction, although everything I've presented now is either presented as an autonomous system or as a trivially driven system, like with constant signals, or put it to a random initial condition and then just relax, like not driving it at all after a kick. The typical situation is that these systems are externally driven in an ongoing way. We have been working a lot on mobility systems and also on electric power grids. both of which are driven, mobility systems are driven by demand and traffic and so on, external weather, and power grids are driven by feed-in variations, for example, by wind or solar power, also by consumption variations and trading events and so on. So there are lots of events which make it a non-equilibrium system. So that's why it's important to not only understand its stationary, its constant or autonomous properties, but also its non-stationary, distributed, and nonlinear properties. Yes, so as I mentioned, this is now again a forward problem. You have the system, you have a model, and our model, because of presentational issues, will have like one parameter or two. But I imagine that the model has actually 10 parameters. And the task is, give me the tipping point or give me the response predicted as a function of all the parameters. And for one parameter, you can always simulate. And for two, you can simulate. But for 10 or 100, you can certainly not simulate, because you would need to simulate a 100-dimensional space of parameters unless you know all the parameters exactly, which is never the case in the real world. So you have a system model with parameters in there. You have a time-varying input, and you want to predict the response dynamics. So again, forward problem, and we have discussed a few things here, and now we are interested in like the response function, in particular bifurcations. When does the system change its qualitative collective response property? And we have been motivated by an observation in power grid models. This is showing the response of frequency, the response amplitude of the frequency of an AC power grid, in which each node, and nodes are consumers or producers of electric energy, in which all of the nodes have three variables, which are the phase angle. If you go to your power plug next to you, like 2.50 meters to your left, there's probably a power plug. There's AC voltage. I believe in Beirut it will be 50 hertz frequency. That's your base frequency. And I don't talk about that frequency. When I talk about frequency now, I mean the frequency. This frequency is the change, the deviation from the 50 hertz. And all the other frequency I will talk about is frequency of my driving signal, which can be any kind of time scale. Okay, and this is the amplitude. You see that the amplitude is distributed somehow heterogeneously in the network in a very simple simulation where only one node is driven. So you go to a stationary operating state, you drive that guy with a sinusoidal signal, G of t, multiplied by a coupling strength epsilon. That's node 1. And you observe other nodes, like, for example, node 63 or node 10, which are like here and there. And there are two lines here. So these are two lines, and these are another two lines. One is gray and continuous, and the other one is dotted. And what you see is, well, it's exactly on top of each other. And one is the linear response theory, like the analytic approximation of the response, given all the full model, which is not surprising. It just means that linear response theory works. And the gray line is the numerical solution, so the exact solution, if you wish. Now, this is true for the frequency. Now it's a voltage variable. So it's another variable for each of the variables, for each of the consumer and producer nodes. And it's heterogeneous again, but in a different way. You drive node 1, and now you look at the voltage variable, which is called En here, okay? The difference in voltage variable. And what you see here is there's a shift. So numeric is the exact result, and the average long-term value is about here. And the analytic approximation, which is our linear response theory, is sitting here. And so there's a shift. And we, although it looks small, it's unclear where it comes from, because here it's not there, right? It's exactly both. It's the same level here, it's the same everywhere. No, here's not. And here it's the same, there's nothing. So the question is, where does the shift come from, and why is it only in the voltage variable? And there's an entire storybook about it. Like Moritz is writing his speech, like finishing to write his PhD thesis this year. I won't go into details. The main question which remains is, where does the shift come from? And if you shift away, what does it mean? I mean, the operating state is somehow a fixed point of your original system. Now, if you drive it, and you drive it by sinusoidal signals, so the average input is actually 0, but the average response is not 0. So there's a change in response, which shifts it to one or the other direction in some variables. And the question is, why is it only in some variables? In which direction does it shift? And when does it stop? Like at some point, if you shift away from a fixed point and you have a multi-stable system, so some complex system, you will go to another stage, right? You will leave the neighborhood of your fixed point. Now you can average that. So this is the shift. This is the shift. It's operating offset, like this is the difference here you actually observe. You would expect this guy from linear response theory, but you get this guy. How does it scale? And we plot here, the inset is the more interesting one. Well, let's, okay, so we start with the main panel. The operating offset is negative, so it gets, the voltage gets more and more negative in a weird way, and then it stops existing, like it drops out of existence here, in the sense that there's no local response anymore. So it's local to the operating state all the way up to epsilon equals 2.5 or so, 2.4, and beyond here it's not near an operating state. So here it's near the original state. And here it's away from state. Actually, here the response is not stationary anymore, but it's not important. The important thing is that it just stops existing. If you plot that in a double logarithmic fashion, and you plot the absolute value here, you see it's somehow quadratic in epsilon. So knowing it's quadratic is not surprising that it's not linear, right? So you don't see it in the linear response. But so why don't you see it here? That's the question. Why, if it's quadratic here, why is it not quadratic there? So general questions to take home from this experiment are: how strong are the shifts as a function of epsilon? Like, can you predict where it is? Can you say it is here, and that is here, and this is here? Why are they nonlinear? Why is it quadratic? And why is it depending on the node? How are they distributed across the grid? Like, why is it a strong response here and a weak response here, where here is the strong response for the frequency? It looks like very weird. And at which epsilon, and that's the most important point, does the system tip, meaning stop existing in a existing with collective dynamics in a neighborhood of its original state? So this is the tipping point. And we call it epsilon c, like the critical epsilon. Yeah, so as before, you have a network, you have input, and you want to know what the response is. It's non-equilibrium, non-linear, networked, distributed response. And so we try to get rid of most of the problems here. In particular, we go to a one-dimensional system. So in general, it looks like this. You have a high-dimensional system. There's an intrinsic dynamics, and you have a driving signal, and the driving signal has zero average. And as for the frequency variables, the response is actually also zero average. But for the voltage variables, it's not zero average. How does it come about? So as I said, to clarify it, we going to consider a very simple setting. We take a system near an existing stable fixed point. I should add stable here. So meaning that if you drive it slightly, it will still be local. And it's a one component driving, and it's also one frequency driving. So you only drive component K. You only drive component K, and you drive it with one given frequency. This is now the frequency, not the power frequency in the grid, but the frequency of driving of the driving signal. Can be anything. Okay, omega 0 is just a variable. And it's not called omega 0 here. So you can now we go to a very, very, very simple example. Not only one component, one frequency, but also only one variable at all. There's only one variable which we call scalar x. There's a nonlinearity f of x, which gives you fixed points. And we skip, like these are all fixed points for all L, but we skip that. So this is the fixed point we're interested in. And here it is. It's minus arc inverse cosine of alpha. Alpha is a positive number, like say alpha is 0.1 or so. What's going on here? Okay. Anyway, so you're sitting at a fixed point. There's also an unstable fixed point over here, but we are considering the stable fixed point. And now, in addition to sitting at a stable fixed point, you drive the system with a cosine trigonometric function, which intrinsically has an average of 0. So you drive it, but on average you don't drive it. What we observed here is as well, you pump it up to strong epsilon, like epsilon equals 6 here. And what you see is the average is actually visible as a shift. So there's shift. This is exactly what we wanted. So we constructed a system where the shift is visible. And also this alpha plays a role. Like we could have said, okay, let's just take cosine x. But we on purpose say it's alpha minus cosine x with a non-zero alpha, because at alpha equals 0, there's a symmetry in the system which cancels the second order term, which makes it vanishing. This means that you only see the lower order approximation, you only see the first order response. And the first order response by construction has 0 shift. So that explains, like, some of the variable have this symmetry. It's actually a symmetry in the potential, or an anti-symmetry in the force about the fixed point. Yeah, you see it here. It's like an anti-symmetric function about this point. And if you have an anti-symmetric function, well, for alpha equals 0, if you have an anti-symmetric function, the shift is exactly 0. So it's not surprising that you don't see it, because the next order will be fourth order, like fourth order in epsilon, which is, well, higher order. Okay, this is just a repetition of what I just said. And now, again, note that this epsilon is already very large, 6. And now I pump it up a bit more. Boom. That's the same variable. I plot x of t minus the fixed point as a function of time. And here you see it's not stationary anymore, non-stationary. Not near x star, and this is near x star. It's near the fixed point. You respond near a fixed point, and also after the transient, which ends about here, like there's some transient trend here, but from time 10 or so onwards, you can say, okay, it's probably stationary, in the sense that it's an approximately periodic response signal. And this is an even larger epsilon. Now you can ask, how large is your shift? How large is this difference? Is the shift as a function of epsilon? And it should be, well, small. For small epsilon, it should be 0. Whatever this is, 0.3 or so, 0.2 for epsilon equals 6, and it should not exist for epsilon equals 8. And again, the questions are, what is the origin of the shift? How does the shift depend on epsilon? And at which epsilon do responses begin to diverge, or the system become non-stationary? Which means that there's some tipping point epsilon c in this interval, right? Somewhere between 6 and 8, you there's an epsilon at which the system responds locally to the original fixed point the last time. And then if you increase epsilon, it's gone. And the rough answers are, the origin of the shift is a nonlinearity of f, and actually not only the nonlinearity, but also some kind of asymmetry. Formally, it's an antisymmetry. It does nonlinearly depend on epsilon and is least second order. And how do we get it? That's the core of today's session. We develop a non-standard perturbation theory. As you can imagine, if you want to predict some function which exists only to a certain point, that means you can't predict it with any kind of standard perturbation theory, because standard perturbation theory is a polynomial in epsilon. If you cut it off at fourth order, you have a fourth order polynomial in epsilon. And the fourth order polynomial by construction exists for all epsilon. So there's no way you can predict a critical coupling strength from that. Okay, so first the nonlinear origin of the shift, and this is now a bit algebra. I'll quickly go through it, but it's really standard. So you approximate your solution by an asymptotic series, and you cut it off somewhere, okay? And here we can cut it off at quadratic order. So you have a fixed point, you have the linear response. This is the linear response function. And then you have your quadratic response function. You substitute this into your original ordinary differential equation. So you get a dot and a2 dot as variables. And of course, the fixed point derivative is 0. So you get this one. And on the right-hand side, you substitute it into f of x. And g of t, this is this one. And then expand in orders of epsilon. And what you get is this. Okay, zeroth order, you only get this guy. First order, you get, of course, the driving signal, which you put in, plus the derivative of f at the fixed point times this first order term, which goes into here. This entire thing goes into f, then you expand in epsilon. And then there's the second order term, which has two terms. One is the second derivative of f, and the other one is this term coming out of the first derivative of f. That's a function of its argument. So there's this one, and then there's this one squared. Okay, and now it's a perturbative approach, meaning that we collect orders of epsilon. Zeroth order is trivial, you just get back your fixed point equation. First order not trivial, but standard in the sense that you can look it up in textbooks and everyone uses it. Second order, you could look it up in textbook, but no one uses it. In part because the standard example textbook problems in physics, for example, are all antisymmetric. Like if you think of the driven pendulum, for example, it's antisymmetric. So second order is 0. So you don't actually need second order to predict anything there. Okay, let's collect the terms. First order, you have this epsilon cosine term, which is here, and then f prime times a1, which is here. And there's a rate of change of a1 on the left-hand side. Second order term is this guy and that guy. And here is the second derivative of a2. The first derivative of a2. So you get these equations. This, you can imagine what happens in the long run. We are interested in the stationary, like long-term response. In long term, you forget the initial condition. So the average of that, if you average this guy over time for long times, then the rate of change of this needs to be 0, right? Because, well, it just goes to some stationary response, meaning that is 0. If that's 0, you can compute a1, and a1 turns out to be also a trigonometric function with an interesting amplitude, like a non-trivial amplitude, which depends on epsilon and, linearly, amplitude which depends on f and on phase shift. So, and the second is, what is the lowest order contribution if the first order is 0? Well, that's typically second order, and sometimes it's higher order. So it's always nonlinear. And now we do the same thing again, more explicitly. We write down the solution of A1. Yeah, just so you can, this is a linear, inhomogeneous ordinary differential equation in A1. So you first solve the homogeneous one, and then you do, for example, variation of the constant and include this cosine driving term to get a general solution which looks like this. So A1 of t turns out to have an argument, an amplitude, capital A1, and there's a shift, which is the phase shift relative to the driving signal, and then there's some second term, but because f is, the fixed point is stable, f prime is smaller than 0, so for large times, this entire thing, I think it's already there, for large times, this entire thing goes to 0 because the f prime is negative. So there's some constant times an exponentially decaying term, and the decay time is given by 1 over the derivative of f at x star. This one on average is 0 because it's a cosine function. It's just shifted cosine. The shifted cosine on average is 0. So the average of A1 is just 0. Now we put A1 into the second order equation here. We put the full solution in here. And then we average. So it's not the same as first averaging, because if average here is 0, if you square 0, it's 0, but it's not that. You square it and then average, okay? So, and then we want to look at, again, long term. So you ignore any term which decays exponentially or quadratically exponentially with e to the something t. And what you get is, after averaging, is an average shift A2, which is A1 squared, which comes from the square here. You substitute that guy here. What you get is a cosine squared term, and the cosine squared omega no t in function of t looks something like this, okay? So the average of that is not 0. average of cosine squared is actually 1/2. Not nice. Okay. And that's why you get a factor of 1/2 here. You get one other half from the second derivative in the Taylor expansion. So it's a total of 1/4. And this gives you 4 here, and there's A1. And again, long term, you get for A2, you get something like that as well, and that decays. So for long term averaging, it's gone. So what you're left over is this guy. So this is the average shift in second order as a function of the amplitude and the derivative of the first and second derivative of f. And then you multiply that by epsilon squared because that was your original approach, and we called it xs because it's like second order, s for second. And that's the lowest non-zero change. So the lowest non-zero change scales quadratically with epsilon as epsilon to 0. And that's an exact asymptotic result and doesn't depend really on what's going on. Okay, we didn't use the fact that f is a cosine function. We just use the fact that it's a stable fixed point. So the shift scales at least quadratically with epsilon, and that means like if you pump up, if you have a system at a fixed point, and now you gradually increase your driving strength, like the amplitude of your driving signal. First, for small epsilon, you wouldn't see anything because epsilon squared function is a parabola. So originally for small epsilon, it's very small. And then once it becomes visible, it very rapidly increases because it's quadratic. Or in other words, if you double the driving amplitude, you quadruple the response shift, which makes it somehow a dangerous thing to have, right? Because every non-symmetric system has that. And it's dangerous in the sense that it's harder to detect because you have this nonlinearity in the response. So this is our observation, it's not the prediction. The measured offset as a function of perturbation strength, and here, as you see, epsilon c, the critical coupling strength is about 7. And it's quadratic for quite a while. Here's 1, 2, 3, 4, 5, like almost until 5 or so. It's indistinguishable from quadratic scaling, and then it deviates and stops existing. So mind that the quadratic approximation will just continue here. Okay, it will not predict anything about the non-existence of responses beyond epsilon c equals 7. So this is the tipping point, and so next question is how to predict the tipping point. You can now go to third order, and the third order turns out to be 0 again. Basically for the same reason that first order 0, you average over periodic functions, which are now high harmonics, but they are still periodic and their average is 0. The fourth order is the next order you can take, and then you have a fourth order approximation. Or you can go to a hundredths order, and no order can tell you the tipping point, because in every order, if you cut it off, as I mentioned in the beginning, every order you cut off, you have a polynomial in that order. Like if you cut off at order 42, you have a polynomial in epsilon with the highest power epsilon to the power of 42, which is a polynomial, and as such, it exists for all epsilon. It doesn't diverge anywhere or doesn't stop existing, so it can't predict the curve. Okay, so standard perturbation theory cannot capture tipping at any order. Okay, so even if you have very motivated graduate students, or you are a very motivated graduate student, and you want to work until 26th order, you will not be able to predict the tipping point. So how to predict it? And Moritz came up with a basic observation, which is why it's nice. It's simple, but it's because it's so simple, it's actually nice. I like it. And the observation is that if you respond locally near to your fixed point, this means you don't go away from the fixed point. If you don't go away from the fixed point, your average velocity, time average velocity is 0, because otherwise you would go away. So time average velocity, rate of change of x, is 0. That's a condition for local response. And then you have the differential equation, and the differential equation says x dot equals f of x plus epsilon g of t. But if you average over one period, then the average of this guy is 0. Okay, the average of this is 0 because it's setting the period, and it has average 0. So it's cosine omega t. So let's say this is gone. And so what you have to have is average over f. The problem is, it looks very simple, but you have to put in the solution of your differential equation, right? It's f of x of t, and then integrate with respect to t. We don't have the solution, but we have an approximate to the solution. And one approximate is the first order approximation. This is a fixed point itself plus its first order correction. But we know it's not first order, so let's put in a second term, which is our unknown thing. Unknown shift. Okay, so this one gives us an expression for x for the shift as a function of epsilon, if we can resolve it, if we can solve this equation for xi of epsilon. Okay. And there are two ways you can do that. I'll present only the simpler one. The simpler one is you choose f such that you can actually solve the integral. Okay. Because this one is known, you can substitute just a cosine with the phase shift. And this is a constant, this is a constant. So it might be, so this has a structure of f of a constant plus a periodic signal with the same period as this. And for certain functions f, this is solvable, in particular if you take f to be a simple periodic function as well. So that is exactly solvable, but typically it's not. And if you can't do that, you have to expand the integral. But you can't expand it just in the Taylor series, because then you get back your original second order perturbation. So let's only talk about the first exactly solvable part. And if you want, I can discuss the more complicated part, approximate part, later in the question session. So you put it in, you put f here, and you solve for this, and you get some Bessel function. Okay, Bessel function is part of the solution of this part of the integral, and then you want to resolve that with respect to x minus x, x plus x shift. And so the shifted deviation is the inverse cosine function of alpha over J0, the Bessel function, evaluated at epsilon times the amplitude of your linear response, minus the fixed point. Now you might be overwhelmed because there are a few steps I skipped here, but the important point is not the steps. The important point is that there's the inverse cosine. The Bessel function actually doesn't matter too much. The inverse cosine has the important property that its realm of definition is not the full real line. It has a bounded set of definition. And it's only defined for values between -1 and 1, or any other subset you want to talk about. So in particular, if you vary epsilon, somehow the Bessel function will vary. And so this guy will vary. And at some point it could touch a boundary, like 1 or -1. In our case, it turns out that 1 is the important one and -1 is not. And so whenever this guy is 1, it defines you the critical epsilon. So the critical epsilon is where alpha over a Bessel function of epsilon times the amplitude equals 1. And this is to say that the critical epsilon is given by the inverse Bessel function of alpha divided by the amplitude. Okay, so this is now the prediction, an approximate prediction of the critical epsilon. If you put in all infinitely many terms here, it would be an exact prediction. Of course, in practice, we can't do that. We could go to higher order. Yeah, let's see what it does. The purple line here, the solid line, is the original behavior of the system, the actual behavior of the system. The green line is the second order prediction, which is works pretty well until epsilon is 6 or 5 or so. And the dashed line is our approximation. So this is it tells you the critical epsilon, but also this guy tells you the shift. It's the offset, this quantity. So this quantity as a function of epsilon, you plot it like here. And this is a dashed line. So you see two things. First, it much better predicts the critical, so the actual shift for epsilon of the order of 5 or larger. Like here, it's much better than the second order. And it also predicts that there is a tipping point, wherever, you know. So there exists a tipping point. That's the most important thing, because any order, as I mentioned, in epsilon, any polynomial can't predict it. So there's a new kind of way looking at this problem. Oh, any question up to here?
Yes, okay.
Good. I'm close to the end now. So take home here is it does predict a tipping point. It also does predict pretty well the offset. Problem here is we have no clue from our formula. Given everything, we don't know how close it is. It's not like in a Taylor expansion, for example. If you Taylor expand a function to 42nd order, you can bound the error by the 43rd order term. So you have an idea of how close you are with your approximation in a given interval. So far, we have no bound for our error. So although we are pretty close here, like a 5% margin, we're predicting the tipping point exactly, and also the offset is well predicted. From only the dashed line, like if you didn't know the full simulation line, we don't know how it behaves. And yeah, I'll show you the motivating model again. So the full model looked like this. So we have capital N nodes. Each node has 3 variables. One is a phase, second is a phase velocity, and the third is the voltage. And there are certain coupling terms in here. As you see that there's a sine function here. And where the driving signal is, there's a sine function, there's no asymmetry here. Whereas here, there's a cosine, and you actually get your asymmetry for various reasons. One is that that there's a voltage variable in here. Actually, there are 2. This might be incorrect. So we had this shift, but only in the voltage variable, not in the frequency variable. And this was our simulation of the system. And these are just, of course, if you observe closely, these are not 60 some curves, but only like 20 or 15. And these are just randomly selected guys, okay? Just to illustrate, otherwise it's overcrowded. So main point is the prediction in theory works also for networks. You can write down the entire story for networks. It's very technical. It just takes a while to coordinate all the indices and so on, but it's the same idea. And it does predict finite tipping. So even for the network here, you have finite epsilon tipping, which no standard perturbation theory can predict. And we can predict that it stops, but it's very limited at the moment because, as I just mentioned, we can't tell how close we are with our approximation. So this is now our approximation. The purple line, the yellow or orange is the actual behavior of the system. You see that the quadratic scaling is pretty well like until here, until epsilon is 1.5 or something. It is sufficient to only consider second order, which is not a problem. Then you want to understand whether there's a tipping point. Yes, there is a tipping point at a finite epsilon. But is it correct? No, it's not, because here the tipping is actually occurring at 7 or so, and like epsilon equals 7, right? And this is approximately epsilon equals 3. So it's off by a factor of 2 or 2.5. Plus, I have no one has an idea of how far it is off. It's actually one of our current tasks to estimate from the model, like given you have a prediction, how wrong can it be? Like what is the bound or what's a typical deviation from it? So here are many open problems. Sitting, do I have a? Yeah, maybe I do have. Sitting right at the frontier of research. It's really something which we have published in September last year. It's a conference proceeding only. We're starting preparing a longer manuscript based on this integral method, which is a new kind of perturbation theory. We revealed a non-trivial average response shift, which is not present in mechanics textbooks and other people's brains, at least not those who we talk to. And these include mathematicians, engineers, physicists, and so on, biophysicists. It's a genuinely nonlinear property. It's, for example, if you have a fixed point always means a locally quadratic potential. It's a stable fixed point. But actually, it's never exactly quadratic if it's not symmetric. So you have a tendency to move in one or the other direction. This is why first it's nonlinear, and second, it also has a preference for a certain direction, which might be relevant for operating any system. For example, we have a loose collaboration with mechanical engineers who are interested in how airplanes fly and how wings wobble. And of course, it's important in which direction the wing on average might move, because it might break one way and not the other. We can quantify the shift by standard second order perturbation theory. That's just observation that no one has seen, but it's not a technical miracle, it's just standard theory. Final order perturbation theory is incapable of predicting tipping points because it's always a polynomial. And we have suggested a new framework for predicting tipping points, which actually comes with intrinsic bounds, like this was the condition of, in our case, the inverse cosine function. Condition of boundedness of the domain of a function. And a host of open challenges, actually much more than we can work on alone. We need to develop useful approximation schemes, like this Bethel function thing was nice, but it's the exception. So typically you can't solve a nonlinear differential equation for one of its arguments. And then you need another approximation scheme, and one scheme is Pade approximation, which is different from Taylor approximation in the sense that it can actually stop existing. In the sense, Pade is based on rational functions, so quotients of polynomials. If the denominator polynomial of the quotient has a 0, that means that the Pade approximation has a point where it does diverge, and that is a predictor for the tipping point. We need to understand errors and bound them ideally, and we want to increase the accuracy of a tipping point. As you have seen, in one example, we have been off by a factor of more than 2. We want to understand the distributedness of the nonlinear responses. I've shown you that the linear responses, the actual responses in the frequency distribute in very different ways than the responses of the voltage variable. And we have no good understanding of why that is so far, basically because we didn't have a look at it. But even if you can formally write it down, and we did that in recent years for linear response only, even if you can write down the linear response, you don't know what that means for the system. You need a way to systematically evaluate your formulas, because these formulas will contain linear response contains sums over n terms. Well, and then you can, of course, substitute numbers and functions in there, but you don't have an understanding of what a sum of n terms means if you have n equals 60, right? Or 1,000. So we want an understanding of, for example, is there something like localization or not? Under which condition does it happen? And things like that. Are there new collective phenomena, which we did find for linear response already, and I would bet that there's more in nonlinear responses. How does the response depend on the network topology? And one topic we have not, or two topics we have not addressed. One is and also not listed here. One is noise. Like if your driving signal is not deterministic, like the sinusoidal driving signal, but more typical, for example, noise. In the simplest case, it's a Wiener process, like Brownian motion. Can you even define a tipping point? Somehow it must be possible, and we're currently experimenting with comparing local relaxation times with first exit times, and we define the tipping point to be the point where these times are of the same order of magnitude. But of course, in general, it's not trivial to define that, because for a given noise strength and a given time t larger than 0, you always have a positive probability that you have already left the local neighborhood of your fixed point. Again, given epsilon and given time, no matter how small epsilon and how small the time, there's a positive probability that your trajectory has already left. So you're already gone. In other words, your critical epsilon would be 0, because there's always some chance you're gone. And now you can ask, okay, where's the probability 1/2 or something? But it's really not trivial to define even what a tipping point in this sense means, although it's intuitively roughly clear that if you drive it with small signals, it will stay local to where it was for a long time. Whereas you drive it with too strong signals, it will leave the neighborhood. Yeah, with that, I'll end my session. Oh, that's one more point. How to predict tipping point from data. I didn't talk about data in the last piece now today. In reality, you often have data, and you don't have a full model. So what do? So say you can record all variables of the system, or even you only have one variable. You have an arbitrarily long recording. How can you infer how that system behaves for larger epsilon if you have measured it for 20 different epsilon values? That's one question. And of course, there are many others related to data. Yeah, with that, I thank you for your attention for today, and also for the last 4 long lectures. I think we spent a total of almost 8 hours together, 7.5 or so hours. I thank my colleagues. Many of them are on this picture, and some are not. The newer ones are not, because it was hiking when times were good before COVID hit. Actually, that's the actual hiking picture next to Dresden. So if you ever want to come, and it's not winter, we can attempt going to nice places in the Dresden area. I would also like to thank you, of course, for your attention, for staying awake for late in the afternoon. And you always are welcome to send me questions. Send it by email. I mean, ask now, of course. Send it by email. Send it by email in like 4 weeks, or whenever you have a question. Also, maybe you want to check out my Twitter. I don't have Instagram or any of that. Here I report basically, report basically on complex systems and nonlinear dynamics, but also on current science and political questions on renewable energy systems and mobility, basically. Currently in Germany, we have a nice discussion, a completely useless discussion of whether or not we should allow, in the European Union, should allow or forbid cars with internal combustion engines based on e-fuels, which are fuels which you can create from renewable energy electricity. Anyway, thank you very much. I'm open to questions, and I'm ready to come back if there's a special session where you want to know something in more detail. Thanks.
Thank you so much, Marc. I guess looking at it, they have a lot to absorb, especially when it came to the perturbation stuff. I think they need to go over things carefully. I don't know if anyone has any question in the crowd, over the audience on Zoom. Okay, I guess not. Well, this pretty much sums up our mini-series with Professor Timme. Unfortunately, it's our last, for the series, but hopefully that would just set the ground for more encounters to come. And I really want to thank him for his really generous, generosity in lecturing and in sharing the supplementary material that were not out in the slides. So that's very much appreciated, Marc. And hopefully we see you sometime in Beirut.
Yes, you're welcome to visit Dresden as well. I'll send the last 2 decks of slides soon, right. Okay, today or tomorrow.
Sure.
And thanks everyone again for asking questions and for staying awake for long lectures.
Yeah, I'll have a disclaimer. It's the first day of the fasting in Lebanon. So people are fasting and somewhat decaffeinated.
Okay. Oh, there are also no coffee. Okay, I see.
Yeah, exactly.
Yeah, I never have coffee. Very rarely. Yeah. Okay, thank you very much.
Thank you so much.
Nice to be with you. And yeah, maybe next time I can join more personally. Thanks.
Thank you.